Okay, so this lecture is a little bit different, and so anyway, uh, I was looking at grades, and I was just kind of also reflecting on this pandemic, and we've been doing distance learning since March, and we're entering, I don't know, what our 9th month here of doing distance learning. It's just been it's been rough, right? And when I was looking at grades, so I'm going to start off not on lecture content, but I did a data analysis on grades here. Okay, so I was looking at kind of the distribution of grades, and I saw this quarter, or this year, there seems to be a greater number of students who have scores less than 70%, which 70% is like passing with a C, and lower than 70% puts students in danger. So I saw that, and I was just kind of thinking, I was just wondering what changes and effects the pandemic have had. And I've tried to do my best to kind of adapt this class for a remote learning environment. I've done my best to try to avoid making this unnecessarily hard or something, because I know the exams are open note and open book, and that's totally fine. But I've also avoided trying to compensate by making the exams unreasonably difficult because they're open note or open book. Okay. But when I saw the grades and I saw more students kind of below 70%, I became concerned. So I decided to do grade analysis. I'm a stats professor after all, so I like doing this kind of data analysis stuff. And so I took a look at the distribution of midterm 1 and midterm 2 scores, and I wanted to see, is there a difference between exam scores this year versus previous years and things like that. All right, so I just kind of want to show you what I found here. All right, so here is a histogram. The histogram of this year's midterm 1 scores are in blue, and they are overlaid on top of the histogram for midterm 1 scores from previous years. Okay, so previous years, this is basically 2018 and 2019, and extra courses and stuff. And so I'm looking at the distribution of grades, and they, in my opinion, when I'm looking at this, they align quite closely. Okay, if anything, this year's midterm 1, a tiny bit, we have a few more people with more scoring 100, scoring hundreds or near 100 or things like that. Okay, but overall, I would say this aligns very closely. This year aligns quite closely with previous years. And if I do a quick check on just kind of summary statistics, such as the first quartile, the median, and the third quartile, the numbers align quite closely as well. So Q1 in the past was 72, and this year it's 74. The median in the past was 84, and this year it's 86, and Q3 is a 93, and this year Q3 is a 94. Okay. In the past, I had a total of 432 students, and this year, between my 2 lectures, I have 153. So this was a good sign. Here's a plot of the empirical CDF. I'm excited to show you this as part of my data analysis, because you guys know what an empirical CDF is now. Whereas, if I try to share any of my data analysis with somebody outside of the stats community, it's just kind of like I have to really dumb down the pictures that I choose, and I just have to say, like, look at this number and look at this number, and they're similar. But here I can show you an empirical CDF. In black is the previous year's empirical CDF. In red is this year's empirical CDF, and we see close alignment between the 2 empirical CDFs, which is a good sign, which indicates that the 2 distributions are similar. Okay, and here I also ran a KS test to compare the distributions, the 2 samples, to see did they come from, do we have evidence that they came from different distributions? And the p-value of the KS test is 34%, which is not significant. And so so the data for midterm 1 and previous midterms one and this year's midterm one scores, you know, they don't provide evidence that the distributions of midterm one scores are different this year than from previous years. So I took that as a good sign that I did not make midterm one unnecessarily hard or easy compared to previous years, which is always a challenge. When you write an exam, it's always a hard thing. And so I was thankful to see this. Okay. Here's the analysis for midterm 2. Okay. So in previous years, this is the distribution of midterm 2 scores. And this is in blue is this year's distribution of midterm 2 scores. Again, very similar. Maybe in previous years, we had a few more people scoring 100, just kind of the flip of what happened in midterm 1. But overall, similar distribution. Okay. And if I check the summary statistics, again, very similar summary values. The median in previous years were 78 versus 77 this year. Q1 78 versus 77, median 90 versus 88, Q3 98 versus 96.5. So similar values as far as these summary statistics go. And again, here's the empirical CDF. And again, we have close alignment between the empirical CDF of this year in red and the empirical CDF of previous years in black here. So, so we have that. And again, the KS test, when I compare the previous year's or old midterm 2 scores versus this current year's midterm 2 scores, I get a p-value of around 35%. And again, I conclude that the data do not provide evidence that this year's distribution of midterm 2 scores is significantly different from previous year's midterm 2 scores. Okay, so to me, I took this as a sign that you know, I managed to write okay exams that were not unnecessarily harder than previous years and not unnecessarily or just much easier than previous years. So these were encouraging signs regarding that. So I was still curious, you know, what could be kind of causing what at least appeared to me a difference in the proportion of students who had scores, you know, overall grades less than 70%. So I decided to take a look at homework grades. Okay. So looking at homework grades, I decided to take a look at how many assignments were missing. Okay, so these are homework scores of 0. So students who just didn't turn in a homework assignment and got a 0, or homework scoring less than 50%. So these I would consider low scoring homework assignments where, you know, maybe a student made an attempt at the homework, or they at least started it, but, you know, maybe only did a couple of the parts and just kind of turned in what they had. Okay, and so so I took a look at that. Okay, and there's quite a big difference between this current year and previous years. So in previous years, generally, almost all of these values are less than 1%. Okay, so as far as who was missing homework 1, about 1/2 of 1% were missing homework 1. Who was missing? But if you look at this year, I have almost 3%, 2.6% missing homework 1. Okay, missing homework 2, you know, around 0.2 of a percentage point we're missing homework 2, and this year we have around 2% of people missing homework 2. Homework 3, we have around 1% missing homework 3 in previous years, and this year, you know, close to 3%, 2.6%. Okay, and then these are low, defined as 50 points or less on homework 1. So 50, so around, you know, 0.7 of a percentage point. And here I got 3% of submissions were less than 50. For homework 2, again, about less than 1/2 of 1% in previous years. And here we're having about 10 times that, about 5% having homework 2 scoring 50% or lower. Okay. And then as far as homework 3, you know, in previous years, around 1% had homework 3 of 50% or less, and this year, you know, around 9%. So about, you know, close, you know, 1 in 11 students had a low scoring homework 3 score. Okay, and if I just did the sheer counts this year, as far as missing homeworks, we had 4 missing homework 1, 3 missing homework 2, and 4 missing homework 3, for a total of 11 missing assignments among 153 students, or 459 assignments total. And then versus previous years, we had a total of 7 missing assignments, 2, 1, and 4, among 432 students, okay, or a total of 1,296, because these are 3 assignments, so we have close to 1,300 assignments. Okay, and then if we look at homework scores below 50, I have 26 low score assignments among 153 students, and versus previous years where we had 11 low score assignments among 432 students. So just kind of looking at this seems like a big jump in terms of students who are missing assignments, students who are scoring low on their homework assignments. But of course, being in the stats department, I can't just say, well, it looks different, so let's see. So I ran an actual proportion test to get a p-value to make sure that my suspicions cannot be explained by random chance. And so for missing assignments, the proportion test for missing assignments, we had 11 out of 459 versus 7 out of 1296. That difference in proportions results in a p-value of 0.0017, okay? So a very small p-value, which means the difference that we see in proportions cannot be explained by random chance alone, okay? And if I look at the low scoring assignments as far as scores that score less than 50%, I get a p-value on the order of 10 to the -9, okay? Which also means that, you know, I would reject the null hypothesis, and the difference in, this should be low scoring assignments, the difference in proportions for low scoring assignments cannot be explained by random chance alone. So what is the explanation here? So, you know, I don't know everybody's life story. I don't know what's happening, but just reflecting on my own feelings and struggles, you know, this quarter with the pandemic and remote learning or remote teaching, and just this general feeling of disconnect with, you know, community and things like that. I feel like we can definitely blame the pandemic and, you know, just kind of the different setup that we're in to, you know, and the effects that it has had on our mental health. I feel like that we can blame that for kind of the difference in kind of homework submission, missing homework rates, and low scoring homework rates. Okay, because, you know, I know there have been days where it's just been a struggle just to kind of get the work done. It's been a struggle to, you know, get out of bed before, you know, my first class is at 10, and there have been days where I roll out of bed at like 9:45 and I put on a shirt and I turn on the computer and I try to jump into teaching. Maybe I shouldn't have told you that, but and, you know, and I've also been lucky enough to have a lot of you I've had for like the entire 102 series. Okay, you know, I think it's important for you guys to get a diversity of teachers, but I'm also honored that you have tried to register for my classes and take them. So you know, I'm also able to kind of look at student history, and, you know, these students who are missing assignments or scoring low on their homework assignments. You know, these aren't lazy students. I recognize these names. These are not lazy students. You know, I had them in 102A, I had them in 102B, you know, and so, and they did well. So I know these are not, this is, so I'm just assuming that this is the result of the pandemic, you know, just being dragged on for like so many months, you know, and just taking its toll on each of us, right? And so I've decided to make just a few changes to my grading scheme. Okay, these are not drastic changes, okay, but just a few minor changes that I kind of want to use. Okay, so anyway, I don't want to have all of these exam scores and stuff posted on CCLE, so you can watch the lecture on YouTube, but if you want to see the numbers again, but what's going to be posted on CCLE will have all of those numbers removed. Okay. So this is going to be the changes that I'm making. So I'm going to make a few small changes to my grade scale. Okay. I've always used a straight scale in the past, and I still believe in the philosophy of using a straight scale. And but this year I'm going to make a couple adjustments to the straight scale. The adjustments are mostly to help the students who are struggling the most. Okay, I think, you know, the students who are struggling the most, I basically have more students than I want scoring lower than 70%, and I don't want to fail all of these students. I don't want to give them low grades where they have to retake the class, or it's going to like slow down their, prevent them from graduating. Okay. So these changes I'm making are mostly to help out these students, to kind of just help them get over the edge, so that they can kind of graduate and move on with life. This quarter has been rough on everybody. So the biggest change is I'm lowering the floor for what's required to get a C, which is what you need to pass and kind of get credit for graduation and all of that. I'm lowering that from a 70 down to a 60%. Okay, and I think this will be enough of a change to kind of help out a lot of students who are kind of struggling and getting their assignments and stuff in. Okay, and so so that's going to be the change, and so so a lot of that will kind of move up, and so a C plus will now go from a 70 to a 77.9. A B minus will go from a 78 to an 80.9. B goes from 81 to 85.9, and B plus goes from 86 to 89.9. Basically, A's will remain the same. Okay, no change to what's required for an A. But looking at kind of the overall distribution of A's and B's, it seems comparable this year to previous years. So it didn't feel necessary to make major changes to the A's and B's. But I'm most concerned about students in kind of this lower range here. Students who probably in any other quarter or year would be fine, but this year finding themselves struggling, and so I'm lowering the floor to what's going to be required to get a C. Okay, so I hope that's okay. I'm also making a small change to the weights of the homework. Okay, so in the original syllabus, I said there's 6 homework assignments, none are dropped. And each assignment is going to be worth 4.5 percentage points for a total of 27%. Okay. And so this is just a very small change. And basically, I'm going to keep homeworks 1 through homeworks 5. I'm not going to make any changes to those. Okay. Those are still going to be worth 4.5%. Just because, for a lot of students who did work hard and stay up late, completing homeworks 1 through homeworks 4 and 5, homeworks 4, which have already been submitted. I don't want to suddenly say all of that effort and labor that you put into your homework assignments is now going to be diminished by kind of reducing the weights of those things. So I'm going to keep those exactly the same as what we started out with. Okay, so I don't want to change any of that. So students who worked hard, I don't want to kind of change that and say, all of that hard work and labor that you put into your earlier homeworks, and some of you have actually made a lot of progress on homework 5 already. So I'm not going to make any changes to the stuff that's already out there. So what I will do is for homework 6, I'm going to just reduce that weight from 4.5% down to 2%. Okay. And the remaining 2.5%, I'm going to just give free points to everybody. Okay. So I'm going to give a free 2.5% to everybody. Homework 6 is only going to be worth 2%. And so, in these last couple of weeks, you can judge and weigh what you have going on in other courses. And if it just feels like it's overwhelming and you say, you know what, I don't want to do homework 6, you can skip homework 6. You'll lose points. You're not going to get the 2 percentage points, but you'll only lose 2 percentage points. Okay. Or if you just put like a half-hearted effort into homework 6 or something, or, you know, you can't really get it working, you know, you might get 50% on it, but again, it's only worth 2 percentage points. So, you know, the impact it'll have on your grade is small. Okay. I wasn't you know, I like homework 6. I have like a personal attachment, not personal attachment, but I like it. And it's a challenging assignment, but I think it's a fun one. And I think it's kind of cool. So I hope you guys do it. But again, don't do it just because I said I hope you do it. All right. Like, you know, make sure you have the kind of the mental bandwidth to do it. And if you feel like you don't want to do it and you'll lose 2% on it, that's totally fine. Okay. Take care of yourself. You know, you'll lose 2%, but it's not that big of a deal. So I'm reducing the weight of homework 6. Okay. So homework will still account for a total of 27%, but as far as homework 6 goes, I've reduced its weight down to 2. Okay. So so just a couple of changes, but I think, and I hope this will help out, you know, students who are kind of struggling, and I hope this will, you know, greatly reduce, you know, students who won't be passing the class. So, because I don't want to do that. Okay. All right, so everything else remains the same, you know, as far as the grading scheme. So these percentage points and that remains the same: 3% for campus-wide participation, and 1% extra credit if you achieve Eagle status on Campus Wire. Okay. Are there any questions regarding kind of the changes or anything that that I'm doing here for the grade schemes? All right. So, you know, with all of this talk of grades and all of that, I just want to kind of pause and just remind you that, you know, what you offer to the world is so much more than your grades or your academic achievements. Okay. You know, I know what it's like to be a good student. I know, you know, in high school, I worked hard to get good grades, to get into a good college, and everybody who's here at UCLA, you know, was only admitted to UCLA because they did well academically in high school or in community college. That's the only way you can get into a university like UCLA. So I think I can relate to, you know, academic overachievers, and I understand just, you know, the feeling. You know, it feels good to get good grades, and it doesn't feel good to get bad grades. And you know, the first university I attended, my freshman year, I actually had to drop out because of poor academic performance. And this was a shock to me because, you know, in high school, the lowest grade I ever got was like a B, and it was, you know, but, you know, it was pretty much A's for like all of my other classes in high school and stuff. And then in college, my fall quarter, I got my first C. And then in winter quarter, I got my first D. And then in spring quarter, I got my first F, and I was put on academic probation. And this was like turning my world upside down. And I ended up having to drop out. And it was very emotionally distressful at the time. You know, maybe I'll tell you my story later, but my father was very, very supportive during that time. And so I'm very grateful for that. But the problem with me was that I had attached so much of my identity with my academic achievements that the way I saw myself was tied directly to how I did academically. And so, you know, when I did well academically, I thought higher of myself. When I did poorly academically, I thought less of myself. And so I think it took that, you know, kind of traumatic experience for me to be able to separate myself from my academic achievements. And so anyway, I just want to say, you know, I don't know where you are, but you are so much more than your grades and your academic achievements. And that was a lesson I had to learn. And I had to learn that one the hard way. But but I want to, just be able to tell you that, you are a person capable of love and compassion and creativity. And, the people that are closest to you, your friends and your family, they care so much more about you and the joy that you have and your love for life that you have than they do about your grades. Okay. It's true. Grades do play a role. Grades play a role in things like grad school admissions, but they're not the only factor that goes into determining grad school decisions. As far as getting jobs in industry, industry rarely cares about your GPA. You're not required to put it on your resume. I mean, you can if you're proud of your GPA, but industry, they generally don't care. And really, once you've worked for a couple of years, 2 or 3 years, your GPA hardly matters at all. And employers are always going to just be more interested in what you've done for your previous company than how you did academically. This is always a little bit of a hard pill to give to students, especially when you're in the middle of kind of all of this academic stress and all of that. And, the last thing you want to hear is somebody saying that like all of your hard work isn't important or something like that. That's I'm trying to avoid saying that. Okay. But I guess I just want to provide a little bit of perspective regarding what role grades and GPA plays in the grand scheme of things. So, tomorrow is Thanksgiving Day, and I know it can be hard to be full of gratitude, especially when there's a lot of kind of hardship in your own life, and you look around in the world and you see so much suffering and so much, grief, and it can be hard to be full of gratitude. But I do want to challenge you, and this, I can't give you a grade for this homework assignment, but I want to say, your assignment this weekend is really to just take the time to reflect this weekend on things or people in your life that bring you joy. Okay, and say these things out loud, maybe out loud to yourself, and just say, I'm thankful for, I'm thankful for, my dog, who brings me joy. Or, if it's a person that brings you joy, please do call and say out loud to that person, I'm thankful for you. Okay. And so I'll start, and I'm going to say, I'm thankful for you, my students, all of you that I'm seeing and looking at right here. I'm thankful for each one of you. Also, if you're watching the video on YouTube, I'm also thankful for you. You're not able to attend live, and that's totally fine. I can still see that people are viewing these videos, and that always feels good to know that your videos are being viewed. And somebody's like clicking like on the videos on YouTube, which is so silly, but it makes me happy. So thank you to whoever is doing that. So I appreciate that as well. But honestly, each one of your students, it's been such a privilege. It's been such an honor being your teacher. For many of you from multiple classes, I'm so thankful that, before the pandemic started, I got to meet a lot of you in person, and we got to have real conversations in office hours. And even after, with all of this remote learning, a lot of you have still come to office hours, and I'm thankful for every single conversation I've had where you've shared a little bit about what's happening in your life, or you've asked me for advice on grad school or advice on career things, which like I'm I'm humbled and honored by just the fact that you would come to me for advice, right? Like you trust me and what my opinions and my thoughts. So I appreciate that. Even when I have to kind of get in an argument with a student about grades and what points does you deserve or whatever, I'm still thankful for those conversations, because it shows me that you guys care. You guys care about your academics. You guys care about your learning. I appreciate each of you, you know, all of you who've turned on your cameras and see me. You know, I'm so grateful for each one of you. So thank you. You know, this Thanksgiving, I'm very, very thankful for the job that I have. I'm very thankful for the being at UCLA, truly working with the top 1% of students. Okay, I know at UCLA, you know, you're surrounded by other brilliant people, and so you can feel like, you know, imposter syndrome and all of this stuff. But truly, you guys are truly the best students that I could ask for. So I'm thankful. I'm thankful for each of you. Okay. All right. So that's what I wanted to say. All right. Worst transition ever. And we're going to talk about hierarchical models now, and we'll get on with lecture content here. But anyway, truly, I'm thankful for all of you. Let me give you some quiz answers, lecture viewing quiz answers. I'll just give you all three of them right now. The answers are A, B, and C. A, B, and C for today's lecture viewing quiz. That should be it. Oh, and thank you for your comments in the chat. No, you guys, I'm the one who needs to be thankful. I'm thankful for you guys. So, all right, ABC for today's lecture viewing quiz, and then let's talk about hierarchical models. I didn't get through all of my slides last class because I also took a long time, I guess, pouring out my heart. So, but anyway, let's, so we talked about the Gibbs Sampler on Monday. And the Gibbs Sampler is a way for us to get values, to draw samples from a multivariate target PDF, right? So you have this target distribution that you want, but it's in high dimensions, it's in D dimensions, and we want to be able to get samples out of it, okay? So X is going to be this D-dimensional vector, and at time t, we might denote that the values in X look like this, and the vector X at time t looks like this, all right? So the what we want to do is we want to be able to produce the next draw, X at time t plus 1, because, you know, we're in a Markov chain, so the next draw is going to be kind of based off of our current draw, and we want to get X at time t plus 1. And with the Gibbs Sampler, the way we're going to get the next draw is we are going to draw kind of each component in X from a univariate distribution. So we set up a univariate distribution, and we are going to, we have to be able to factor the joint distribution of all the terms into a whole bunch of univariate conditional distributions. We're going to have distributions of one variable at a time, which have been conditioned on basically all of the other values. And so for the first term, x1 at time t plus 1 will come from the conditional probability distribution of x1 given all of the other values, which will be x2 at time t all the way up through xd at time t. When we look at the next value, x2 will be drawn from the conditional distribution of x2 given, and we're going to use the newest value for x1, which will be x1 at time t plus 1. And, you know, oh, this should be x3. That's a typo. The newest values that we have for every other value, which will be x3 at time t all the way up to xd at time t. Okay. X3 at time t plus 1 will be drawn from the conditional distribution of x3 given x1 at time t plus 1, x2 at time t plus 1, and then because these are the newest values that we have for x1 and x2, we haven't drawn the newest value. I mean, we haven't drawn a newer value for x4 than x4 at time t. So x4 at time t is our newest value for x4, and we use the newest values that we have for all of the other variables which haven't been redrawn yet. So this is going to be the conditional distribution here. So x, the ith value in x at time t plus 1 will be the conditional distribution of x sub I given x1 at time t plus 1 through xi minus 1 at time t plus 1. So all the values that come before x sub I, we will have updated to time t plus 1. All the values that come after x sub I, so that's x sub I plus 1 all the way through xd, we haven't drawn new values yet. So those are all going to be the newest values that we have are at time t. The most recent values we have are at time t. Okay, and we continue this until we get to the dth value in x. Okay, x sub d will come from the conditional distribution of xd given everything else. All right, so that's the Gibbs sampler. And the hard part is being able to factor the joint distribution into a whole bunch of these conditional univariate distributions. Okay, and so the Gibbs sampler works very well for what we call a hierarchical model. Okay, and the hierarchical model is set up using conditional distributions. Okay, and so because it's set up using conditional distributions, having to kind of derive or factor out the conditional distributions won't be necessary. Okay, what we can do is, we'll set things up in this hierarchical fashion with conditional distributions. And so when it comes to setting them up, the conditional distributions are already there. All right. So what we're going to do is we're going to revisit the Bayesian beta binomial baseball example. Okay. And so when we did that, we said every player has a random variable theta, which is going to be their batting average. Okay. So we have theta, that's their batting average. And the batting average we can just think of as the probability of getting a hit when the player has an at-bat. Okay, what's the probability that we see a hit during an at-bat? And so there's some prior distribution for theta. Okay, and what we did, so if we go all the way back to lecture 1 or lecture 1-1, we said this was our prior distribution for theta. Okay, in that almost all of the values are going to be above 0.2, and almost all the values are going to be 0.3 below 0.35. Okay, because that's what we said. We said if you study baseball statistics, basically if you have a batting average below 0.2, you're going to get cut from the team. So nobody should have a batting average below 0.2. And the greatest batting average of all time is around like 0.366, and really having a batting average above 300.3 is quite challenging to do. So we ended up choosing these shape parameters 81 and 219. These choices of 81 and 219, however, are a little bit arbitrary. And we chose them because they produce a distribution with properties that we like. Okay. So what we do in a hierarchical model, okay, so the parameters 81 and 219, these are parameters of the prior distribution. They are alpha and beta, 81 and 219, or whatever numbers we choose. They're called hyperparameters, all right? And when we set up a hierarchical model, what we're going to do is we're not going to choose these values arbitrarily. We're not going to just say, hey, let's use 81 and let's use 219 because it gives me this distribution that we like. We're going to treat alpha as a random variable. We're going to treat beta as a random variable, okay? So rather than me saying I want to pick 81, I'm going to draw a value for alpha from some kind of random distribution or some kind of random process, okay? And rather than choosing beta is 219, I'm going to draw beta from some kind of random distribution. And so these are now treated as random variables with their own random distribution. So we say the hyperparameters, alpha and beta, have their own kind of prior distribution. All right, and I'm totally serious here. The prior distribution for the hyperparameters of alpha and beta is known as the hyperprior. Okay, it's known as the hyperprior. It's the distribution. The hyperprior is the distribution that will produce alpha and beta, which are the parameters or the hyperparameters that determine the shape of the prior distribution of theta. Okay, and again, theta is going to be the batting average, which is then used to determine whether somebody gets hits or outs. Okay, now if alpha and beta come from a hyperprior distribution, okay, this hyperprior distribution might have its own parameters, and no joke, those would be called hyperparameters, okay? They're called hyperparameters. And we can choose the values for the hyperparameters ourselves, okay? And generally, when you get to the hyperparameter level, you can kind of choose these arbitrarily. Or if you want, you can also put another hyper distribution on top of that, and you would have the hyperprior with the hyper parameters and things like that. And it can go on to infinity. Generally, you stop after a couple of layers of this hyper distribution stuff, right? So I've got the prior distribution and I've got the hyperprior distribution, and oftentimes we'll just kind of stop there, okay? But by removing ourselves, taking one layer of away, even though these values up here are arbitrary, it's going to allow for alpha and beta to be selected randomly, which will then determine the prior distribution, and that will determine theta randomly. And so you're basically giving it more and more freedom the more layers that you remove, right? So basically, you as a person can make individual choices. You know, you have your parents that have greater influence on you, and then your grandparents had influence on your parents and indirectly have influence on you. But basically, the influence of your grandparents is now is lessened, you know, with kind of each generation. And similarly, our arbitrary choices for the hyperprior distribution, the hyperparameter distributions, even if they're chosen arbitrarily, you know, their direct influence is lessened because of kind of these layers of removal here. Okay. The values for alpha and beta, you know, we selected were 81 and 219, okay? We often can think of these things as pseudo counts. So prior to kind of seeing the data, you know, we can pretend that, you know, some baseball player who qualifies for the major leagues have, quote, an 81 hits or 219 outs. And these aren't actual data values, but they're kind of imaginary counts of successes and failures. And basically what we do is when you have these pseudo counts and you observe more data, you add the results of your observed data to your to your pseudo counts, right? So if we observed, you know, 10 at-bats where we had 5 hits and 5 outs, we kind of just added 5 to 81 and 5 to 219, and our posterior was 86 and 224. What we're going to do to kind of facilitate this prior distribution setup, the hyperprior distribution setup, is rather than trying to draw alpha and beta directly, we're going to draw a value omega, okay? And omega is going to represent the mode or the peak of our beta distribution, okay? And so the mode of the beta distribution is alpha minus 1 divided by alpha plus beta minus 2. And so right now our value for omega is 0.2685, okay? And that seems to be a reasonable value to use for batting average, okay? And what we're going to do is we're going to, rather than drawing alpha and beta directly, is we're going to treat omega as the random value, okay? And so omega is going to be this random value, and we're going to determine the values alpha and beta based on our choice of omega, okay? The random draw of omega will determine alpha and beta. So rather than drawing alpha directly and beta directly, we're going to draw omega, and we're going to plug in omega into this formula or equation to get the value for alpha and beta. So alpha is going to be determined. Once you have omega, alpha is determined, okay? We do omega times k minus 2 plus 1, which is just kind of, if you substitute this, if you solve for alpha in terms of omega here, this is what you would get, okay? You get alpha is, where k is the sum of alpha and beta. K is kind of 300, 81 plus 219 is 300. So if you do alpha is equal to omega times k minus 2 plus 1, you get 81. And then I forgot to put in a beta here. Beta is going to be 1 minus omega times k minus 2 plus 1, and you get 219. So again, so instead of drawing alpha and beta directly, we're going to draw omega, and omega will determine what alpha and beta are. Okay, So omega is going to be the peak, kind of the proportion, the peak batting average. Okay. And so we're going to say omega itself comes from a beta distribution. Okay. So we have like this is the Hyperprior distribution that's going to determine omega. Okay. And so we need to figure out the hyper parameters of this beta distribution, which will be alpha sub omega or B sub omega. Okay. A sub omega and B sub omega. Okay. And we're going to just kind of have to choose these arbitrarily. We're going to also choose K arbitrarily here, K being the sum of alpha and beta. So we have to make some arbitrary choices, but this will remove us a little bit from the process, so that our arbitrary choices. So when we chose 81 and 219 directly, those arbitrary choices had quite a strong strong impact on the resulting posterior distributions. Now that we're going to choose kind of a layer removed from it, our choices will be less impactful, okay? And the data will have a greater influence now. Okay, so here is kind of the hierarchy, okay? K is arbitrarily selected constant, okay? A sub omega and B sub omega are also arbitrarily selected constants, okay? Omega is going to be drawn from this beta distribution, where this beta distribution is the Hyperprior distribution. It's the Hyperprior, and we're going to draw omega. Okay, so omega is a random value drawn from this distribution. Alpha is going to be determined, once we get omega, it's determined by K and the random value of omega. We say alpha is omega times K minus 2 plus 1. Beta is 1 minus omega times K minus 2 plus 1, okay? And these terms, alpha and beta, are determined randomly by the choice of omega. And these terms go into the prior distribution for theta. So the prior distribution for theta will be a beta with shape parameters alpha and beta. So theta come from the beta distribution. And then when we look at the actual data values, the data values are just whether the player got a hit or they got an out. Those are just Bernoulli draws. Those are basically coin flips, okay? And so the y sub I values that we get from the Bernoulli are going to be Bernoulli draws with parameter theta. Is this okay, this hierarchy here? The diagram, this is taken from Doing Bayesian Data Analysis, Chapter 9. The idea here is you've got this beta distribution with shape parameters alpha or A sub omega and B sub omega that determine this. And from this beta distribution, we draw a random value W or omega, okay? Omega determines the value alpha and beta that get used in this beta distribution. And from this beta distribution, we draw the value theta. And this theta will factor into the Bernoulli distribution, which will produce our values y sub I. Okay, once we have this hierarchical model, then we can kind of elaborate on this, and we can say, we can start simulating the hits and outs of multiple players, players 1 through 1, player 2, player S, so on and so forth. And I think we're going to have to put this on hold, and we'll continue talking about hierarchical models and Gibbs sampling after the break, when we see you guys on Monday. Okay. So so that's it. We'll end here for today. Have a happy Thanksgiving, you guys. Truly, I'm thankful for you as my students. I hope you guys have a good weekend. Stay safe, stay healthy. We enjoy your time this weekend, and we will see you guys on Monday. So so we'll end there.